Okay, so this is a video solution to problem 2.9 in Griffith's Electrodynamics Introduction to Electrodynamics 4th edition. And problem 2.9 reads that if we suppose the electric field in some region is found to be vector equation E is equal to k r cubed in the r hat direction and is in spherical coordinates with k equaling some constant, then A, find the charge density rho, and B, find the charge enclosed in a sphere of radius r centered on the origin. And we're going to do this in two methods, or more than two methods, but we're only going to do it in two because the problem reverses that way. So, something important before we can begin, this is a problem that requires application of Gauss's law. And Gauss's law is fairly simple, right? Gauss's law states that over a closed surface, right, if we take the integral over a closed surface of the electric field, we will find all of the charges within that surface and the sum total of those charges over the permittivity of free space, epsilon naught, which is another constant, which I will not define, but it's not necessary to in this problem, so that's okay. So we know this, right? This is fine. This is Gauss's law. Now, an important thing to recognize, right, is that this here, right, we can apply the divergence theorem to. So we know that any closed surface integral of some vector equation dA will also be equal to the open volume integral of the divergence of that same vector equation, d tau, right? The non-vector volume element d tau. We also can put Q enclosed in terms of, without epsilon naught, we can put Q enclosed of rho, which we are trying to find, right? And so we can find Q enclosed if we know that the volume integral of rho d tau, right? And rho is a scalar. The charge density is a scalar. It may be a function. It may just be a value. Depends on the problem. But we do know that it can be a function, right? So we know that this is true. Now, we also know that if we were to divide this by epsilon naught, then the result would be the same since we can apply linearity, right? If I was to divide this by epsilon naught, I could apply linearity and recognize that Q enclosed over epsilon naught is equivalent to just rho d tau. Okay? So far, so good. And so we can then recognize that there is a lot of things set equal to each other here, right? And we can put that all in one format, okay? And so we'll start with knowing that, Q enclosed, right, over epsilon naught is going to be equal to the surface, the closed surface integral E dot dA, right? That's this up here, okay? And we also know that this, thanks to the divergence theorem, will also be equal to the non-closed integral of the divergence of E d tau, of the E field, the electric field d tau. And then, this is a volume integral, right? And then we also know that this Q enclosed over epsilon naught is now equal to this, which can be shown with and without the linearity before solving. So in this case, we will just keep it on the inside, right? Rho over epsilon naught times d tau. Excuse me, I'm very sick. Apologize for the sniffling. I actually have a very bad head cold. Thankfully, I'm not on camera, so you can't notice that I'm sweating profusely. Anyway, this volume integral and this volume element, this differentiable volume element, will be the same for this problem, right? They're going to be over the same volume, so we can recognize that if we were to take the direct opposite derivative of both of the sides of this equation, this one specifically, right, that we would end up with what is known as the differentiable form of Gauss's law, okay? Nope, no d tau, okay? And so we end up knowing that the divergence of the electric field is equal to the charge density rho over epsilon naught, okay? And that's an important aspect in solving this problem. So I'm going to leave this here for just a second in case anyone needs to finish the understanding and looking at it. Okay, now we go back and we see that we are trying to solve for charge density. We know that our equation E right here, right? This is our equation for the electric field. And in this problem, right, you'll notice that before we're given some denotation of the shape that we are integrating over, the space or volume, right, we're not in this first one. And that's because there's just a differentiable form, right, which we found. And so we don't actually need a space or a region to do it for, right? It just says some region up here. That region has no matter in finding the charge density in this specific equation. So what we do need to know, however, if we find the divergence, there's a formula for finding the divergence of a vector field. And in order to save a little time, we'll recognize that that formula for the divergence of some vector field is in 3 parts, right? I'm going to bring our equation for the electric field down here. Okay. And we know that the divergence of some vector field, V, we'll say, for random's sake, it actually has 3 parts, right? That all include some version of the derivative with respect to each of the spherical hat directions, okay? And so it'll be something A1 with this involved, DDR. A1 is a function of DDR. It's not accurate, but just to save time. So, and it's in 3 parts, and this one will be del del theta, and the third one will have some version, some function del del phi. But we'll notice, right, that if we do this divergence, what will happen is we'll get everything involved with the r hat component in here. And then when we do the rest, we're going to end up with 0, because this equation for the electric field has nothing in the theta hat direction, as well as nothing in the phi hat direction, right? So there won't be a component to take the derivative del del theta or del del phi of. And if there is, in a sense, right, you could say that you're taking the derivative with respect to theta of 0 plus the derivative with respect to phi of 0, right? And that's just going to give you 0, right? So that makes these unnecessary. So in this vector equation, we know that the first portion, and not the latter two, excuse me, is going to be 1 over r squared times del del r acting on r squared times our VR component, right? And so if we apply all this to our electric field, we find we will have 1 over r squared del del r of r squared times k r cubed, right? And that's what we're going to have here, and that's going to be equal to the divergence of E. This is just this, right? And so if we do this, we find adding these together gives us r to the 5th, k r to the 5th, right? Keep that constant in there. And we keep this r squared out in front, 1 over r squared. the derivative of r to the fifth with some constant. If we pull it out, just r to the fifth, we get 5r to the fourth. So we have this is equal to 5k r to the fourth over r squared. Okay. And we end up with 5k r squared, right? And so that's the divergence of E. Now, you'd think we might be done, right? Because we found that this is equal to rho over epsilon naught. But we have to recognize that we're looking for just rho. So we have to take this and set it equal to rho over epsilon naught, right? And we multiply both sides by epsilon naught, right? And again, this is the permittivity of free space. It's important to know that. Okay. And we end up with that our charge density that we were looking for is 5k times epsilon naught times r squared. Okay? And so that is the solution to part A. Okay? Okay, so what's the next part? The next part tells us to find the charge enclosed in a sphere of radius r centered on the origin. And we're going to do this in two methods. Okay? And so I can understand looking at this and thinking when it says do it in two methods, right? I can understand why it's a little confusing. Always rely on the formulas given in the textbook because they're very straightforward in Griffith's Electrodynamics, Introduction to Electrodynamics. They're very, very straightforward, right? And they're almost straightforward to a fault in that they're not going to reference many things unless they're directly referencing equations, right? And so you should know that most of the time, they're frequently just referencing that you need to apply those equations. So when it asks us to do this in two methods, it wants us to use this, right? Simple enough, right? And so we have lots of different things here. We have, for one, right, we can find, we can do it this way with the Gaussian, right, and set it equal to Q enclosed, because we have the electric field and we can find dA over the space given, right, over the volume given, which is a sphere of radius r, right? Okay. We can also do this because we know the volume element of a sphere, and we can do this with the same volume element of the sphere because now we have rho, right? So let's do that. Let's do this one right here, the closed surface integral, and we have to remember that this is set equal to Q enclosed over epsilon naught, right? And so we'll write that. So let's start on part B here, okay? Q enclosed over epsilon naught is equal to the closed surface integral E dot dA. Okay, so again, very important application of Gauss's law here, right? We have to recognize what we're doing and what we're referencing. And in this case, it never hurts to draw a photo of exactly what we're working on. That's what I've found. And so we are working on a sphere, right? This is a circle, but I mean, you recognize that this circle will also have a three-dimensional space, right? And so to find the surface integral that we want to do, we need to know what will be changing if we consider this sphere a surface, right? And so if we think about it, if this surface goes all the way around and it always stays the same, all the surface stays the same length away from the origin, which is where it's centered, right? Then the one thing that's not going to change, the one thing that will have a zero differentiable element, right, is going to be dr. And r is just the magnitude, right, of the line here that goes all the way to the edge. And we know that dr is 0, which means that r is going to be a constant value. And they tell us in part B, right, a sphere of radius r. Okay, so we know that r is going to constantly have value r. Okay, we know that E is kr2 cubed and in the r direction. Okay, and we know that our differentiable area element here, right, we're only going to include what's in the r hat direction, and the r hat direction right? We'll have d theta and d phi, and we know that these are going to be some value, right? We know that d theta will have limits of integration. When we put it in this integral, mind you, theta is going to go from, let's see, we go from the top, the positive z direction, all the way to the bottom, the negative z direction, doing a whole half circle. That means we're going to go from 0, well, we'll go from 0 to pi, right? Because a half circle is a length pi in degrees, or, well, in radians. And we know that phi is going to go completely around the circle, starting in the x-axis. That's supposed to be an arrow, but you see the difference. We start at 0, and we go completely to 2 pi, okay? And then we just put it all together, right? We know that dA's area element, and dA is just to represent a surface, right? dA's area element with just the r hat, because we're dotting them, right? The r hat will be r times r sine theta, right? Because dr will not be included, so we don't use the components in the dA area element. So r times r sine theta, d theta, d phi, okay? And that is the r hat direction. And so we will dot these together, and we'll find that E dot dA is going to be K times r cubed times r squared, so that's kr to the 5th, times sine of theta, d theta, d phi, okay? And from here, all we have to do is put it on the surface integral using these limits of integration, right? And so we'll do that now. Always remembering what we are setting this equal to, okay? We are trying to find charge enclosed, but this integral is set equal to charge enclosed over the permittivity of free space, epsilon naught, okay? And so we find that theta goes from 0 to pi, and the part of theta that we are going to integrate, the only thing that's reliant in the equation is this sine of theta, right? And r to the 5th, right, we have to recognize r to the 5th is constant, r equals r, right? And so nothing's going to integrate this. This will not change in value. So we're just going to plug in r, capital R, where the little r's are, and then we can pull them out as a constant. So I'm going to do that first, right? This is capital R to the 5th, and that comes out. We can also apply linearity to this constant k, right? And this is to denote that k is constant. So I'm going to pull k out, okay? And this is our integration portion with object relative to theta. Then we have phi as it goes from 0 to 2 pi, and we recognize nothing in here is relevant to phi except d phi. So effectively this is 1 times d phi in the integration. We'll perform both of these. We end up with negative cosine of theta here from 0 to pi. And we multiply this not only by the constants we pulled out, but by phi, the result of this one, phi from 0 to 2 pi, right? And this is equal to k times r to the 5th times negative cosine of pi minus cosine of 0, right? And then we're going to multiply by the result of phi, which is 2 pi minus 0. This is negative times negative 1, so I get positive 1 here. Minus minus gives me plus cosine of 0, which is 1, so this becomes 2. 2 pi minus 0 is 2 pi, so I get 2 times 2 pi times kr to the 5th, and I find that Q enclosed over epsilon naught, remember what we're doing here, is equal to k, well, I should put the numbers in front. 2 times 2 pi is 4 pi, times k r to the fifth. Okay? And we are just looking for the charge enclosed, so we're going to multiply epsilon naught to both sides, and we find in the first method the charge enclosed will be equal to 4 pi epsilon naught k r to the fifth. Okay? And so this is our answer that we should find for part B and also in the next way that we solve. Right? So let's go back up and find another method. Right? How about we directly integrate rho over epsilon naught? Okay? And so I'll pull that down here. We know what rho is, right? We found that. Rho is 5k epsilon naught times r squared. So let's just write this out. Rho over, well, no. The volume integral of rho d tau is equal to q enclosed over epsilon naught again, right? We found that rho was equal to 5kr squared times epsilon naught, right? Excuse me. Well, we know that this is an important aspect, not to mess it up, right? Because we want the epsilon naught to be there when we want it, but when we're solving for q enclosed, we do not want that, right? And let me just make sure we didn't make a mistake there. Actually, that would be important. So if I go back here, the mistake that I'm worried about making right now is that I didn't move this epsilon naught correctly in reference, right? We know that q over this is this, and so we have epsilon naught. This was the first portion. This was performed correctly, right? And then we divide this. No, wait a minute. We set it equal to rho over epsilon naught and get rho. There was no epsilon naught in it. Yeah, that's correct. Okay, so we find rho here, right? We had rho. Rho was 5k epsilon naught r squared. So let's just get that down here. 5k epsilon naught r squared. And now we want to find d tau, right? So again, we know the first two portions of this because again, the volumes are going to be the same, even for the dA, right? But we have d tau, which is the volume element. And the volume element's just a little bit larger. We just need to know what r is changing from. And again, it's only going to go from the center, the origin, all the way out, and all the way out is a length r, capital R. And so now we use all three portions, right? All three elements, what is it? Components of each of the different hat directions in d tau, the area element. And we get this times r squared sine theta d theta, nope, dr d theta d phi, okay? And then we know we're going to use the same limits of integration that we did for this surface, right? Theta goes from 0 to pi, and phi goes from 0 to 2 pi. And then we're just going to integrate for r from 0 to capital R, okay? So once again, q enclosed, and that equals our three things here. We have r equals 0 going to capital R, and if we combine all our r's and pull them, we have r squared here and dr, so r squared dr. Then we have our, well, gotta remember to put our constants out first, right? The constants for this one are 5k epsilon naught, so let's pull all those out. 5k epsilon naught, okay? still equals Q enclosed. Excuse me. Theta goes from 0 to pi, and the portions of this equation that matter for that is sine of theta d theta. And then finally, the third, phi equals 0, and it goes to 2 pi, and again, nothing but d phi here, okay? And so we do each of these individually. We get that Q enclosed will be 5k epsilon naught times result of this. Oh, wait, messed up here. R squared times R squared, that's R to the fourth. Sorry. All right, that's an important distinction there. It's because these two are multiplied together. R to the fourth integrated will be R to the fifth over 5. So we have R the fifth divided by 5, and we go from 0 to R for that, times the result of this, which we found was 2. Remember, the exact same integral as dA becomes negative cosine. That negative cosine becomes value 2, right? And then the same for our phi, which is 2 pi, okay? And we get 2 for this, and then next we get times 2 pi, okay? And this becomes R to the fifth over 5 multiplied by 5k epsilon naught, or 5s are going to cancel out, multiplied by 2 times 2 pi, which is 4 pi, and we find that Q enclosed is equal to 4 pi k epsilon naught times R to the capital R to the fifth, okay? And I believe that is the exact same answer that we found using the first method. Yes, you can compare them, right? 4 pi epsilon naught k R to the fifth, and the same down here. And so that is how we find Q enclosed in two different methods, okay? And this has been the solution to 2.9 of Griffith's 4th edition of the Introduction to Electrodynamics. This has been Big Tony. Thank you, Professor Salik, for this opportunity. I will see you in class on Wednesday. Bye-bye.